Okay, so it's 12 o'clock on my computer. Hello, everyone. Thank you for joining us today for the webinar with the title, How to Forecast Germany's Large PV Portfolio. My name is Aleksandra Radwanska, and I'm the International Business Development Manager at Next Kraftwerke. And today I'll be holding this webinar with my colleague, Linden, who is the data analyst in the trading department. The presentation today is expected to last 30 minutes. After that, we'll have 30 minutes at the end for the questions and answers. Before we start, I have a few housekeeping conditions to cover. So first, today's webinar will be recorded and it will be available together with the presentation on our website. You'll obtain the link to access this materials in the follow-up email. And secondly, you remain muted during the webinar. Nevertheless, we would like to hear your questions. So feel free to submit any questions that may arise. And please use for this the Q&A function. I highly encourage you to ask your questions during the presentation, because we'll try to to be very concise and very time effective. So we'll rather cut taking the questions at the end of the presentation. So if you have any question, please try to ask it on the spot. We'll be monitoring the questions during the presentation. And as I mentioned, we'll answer them at the end of the webinar. Due to the time constraints, we apologize if a question is not addressed during the webinar. In this case, we may get back to you afterwards individually, but we also encourage you to contact us on the webinar at nextkraftwerke.de. We'll also show you this email address at the end. I hope that this webinar will be insightful for you and you'll gain new knowledge that is applicable in your business. So let's start. Let me at the beginning introduce you to the agenda of today's webinar. At the beginning, we'll get to know very briefly Next Kraftwerke. Then Martin will lead you through our photovoltaics related services. He will also highlight the importance of accurate intraday forecasts and its utilization on the intraday market. Then Martin will take you through the process of how we develop our photovoltaics forecasts. And at the end, we'll summarize the webinar also with answering questions from your side. So let's jump to the first point. Let me briefly introduce Next Kraftwerke, what we do and who we are. So we are the operator of the second largest virtual power plant in Europe. And we operate a mixed asset VPP, which is currently aggregating over 9 gigawatt of installed capacity and consists of almost 10,000 energy generators, energy consumers, and storage units. We are active currently in 8 European countries and serve 8 transmission system operators by delivering balancing services to them. We manage over 9,000 assets without owning them, as I mentioned. So we, in fact, take over the commercial activity of buying and selling plants in feed or offtake on power markets, and we represent them as their balancing responsible party. Additionally, we offer to the independent power producers access to the day-ahead and intraday markets, as well as the, for example, optimization of generation or consumption schedules, which help them to increase their revenues or decrease energy purchase costs, respectively. Apart from that, apart from being the operator of the virtual power plant, we are also the global VPP platform provider. So globally, not only in European countries, we enable aggregators, utilities, traders, and independent power producers to build their own virtual power plant. We offer them our VPP as a service solution, which is called Nemox. And this solution enables them to monitor a portfolio of distributed energy resources or variable renewable energy sources in real time, steer the units individually, but also dispatch whole pools of technical units. Additionally, this infrastructure is capable of reliable and real-time steering of these devices to, for example, commercialize their flexibility on ancillary service market, especially delivering the products such as FCR, AFRR, and MFRR. So as a result, the VPP operator and owners of the DER or renewable energy sources that are connected to this virtual power plant utilize their flexibility of their assets to, in fact, capitalizing on supporting the energy transition by protecting the grid against the fluctuations that are associated with the volatile energy sources. Now, let me pass over the microphone to Martin Linden, and let's focus on our PV-related services.
Yes, thank you very much for your kind introduction, Aleksandra. My name is Martin Linden, and I work as a data analyst in the trading department of Next Kraftwerke, and I will guide you through the rest of the presentation. So first, I'd like to start with our PV-related services. Now, at first, I'd like to give you a short overview, a quick overview of our current portfolio. As you can see, our portfolio is very large in Germany. Here we aggregate overall roughly 5,000 units, which makes up about 4 gigawatts. Just to put it in perspective, this is about the size of 4 nuclear power plants. And you can also see that our portfolio in Poland is currently also quite large, and our PV portfolio in the Netherlands is increasing as well. Now, regarding our PV-related services, at our PV plants, we usually install a machine-to-machine communication device. And this device allows us to collect live data, temperature, and other relevant data that can help us for our forecasting services. This device can either be our own device. We have a so-called Next box, which is a technical unit that we can set up at a certain unit at the site, or we can also collect this data throughout APIs to existing data loggers, for example, at a photovoltaic plant's inverter. And if we have the possibility to steer a plant, in that case, we can also offer PV curtailment services. This can make sense to reduce the cost of operating a PV plant in case of negative short-term prices. So, for example, in Germany, there is a scheme in which the distributed system operators are no longer obliged to pay a market premium, which is part of the subsidy scheme in the case of 6 subsequent hours of negative day-ahead prices. So at Next, we can, in those cases, shut off or decrease the in-feed of the PV plants, and in that way we can reduce the costs of operating a PV plant. We also offer bilateral PV power purchase agreements. This can make, those PPAs can make sense for plants that don't fall into any subsidy scheme, or plants that have reached the end of their support scheme, and if the operators are looking for a fixed price for the upcoming years. And as Aleksandra has already mentioned, we also provide virtual power plant as a service, our so-called NEMOX software. And one module of that software is also the monitoring and visualization of PV plants. We can also offer the service of PV forecasting. One example you can see here on the right-hand side, the lower picture, it's the PV plant Monte Cristo, which has a capacity of 58 megawatts, and it's located in the Dominican Republic. Now, regarding the live data that we can collect, we already have put in place a standardized interfaces to a vast amount of common systems. Here you can already see a preliminary list, and we are extending this list over time, also for the future, so that we are able to collect the live data in a very fast and efficient way. And how we actually make use of this live data and what effect does PV technologies have on short-term markets are the topics that I will get into in the following. So why accurate intraday forecasts matter, especially on the short-term markets, this will be the next topic. I'd like to present to you the case of Germany and how we believe that, accurate forecasts are very important for the short-term market. In Germany, we at Next and also many other power traders are also so-called balancing responsible parties, BRPs, and that way we are responsible for the balancing of a portfolio. So what we do as BRPs is we try to actively reduce the deviations between our submitted schedules, so the schedules that we basically retrieve via trading on short-term markets, and the expected physical generation or consumption. And by reducing this deviation, we try to reduce the forecasting error. And that way we also reduce the imbalance volumes, which then again reduces the imbalance costs of running a PV plant. And in Germany, we are active on the short-term market, mainly on the Apex spot wholesale market, the power exchange. And here we have, for example, the Dayhead auction, which usually takes place at noon. So just 11 minutes ago, there was the Dayhead auction for tomorrow. And here we have traded a large proportion of our PV, of our expected PV in feed. Then there is the intraday auction in Germany, which is a local auction that happens at 3 p.m. And this is the first time that we are able to trade quarter hourly, so 15 minutes products. And those 15 minutes products are way better to mirror and to reflect the volatile in-feed of PV and also of wind technologies. After 3 p.m., so after the intraday auction, is the start of the so-called intraday continuous trading. And here we have a gate closure at 30 minutes before the delivery time, at least for Germany. But then we also have an extended trading possibility within one control zone, even until 5 minutes before the real time. This feature is existing because in Germany it's structured in 4 control zones. And on the right-hand side, you can see a very typical pattern for day-ahead prices in the upper graph, and in the lower graph, you have typical pattern for quarter-hourly intraday prices. Regarding the day-ahead prices, you can see how you can see a very large impact of the PV feed in Germany and how it creates some sort of camel-like price pattern. Because in the middle of the day, the PV in feed is usually the strongest. So in that way, the very cheap power from photovoltaic can basically push out more expensive technologies such as gas power plants from the market, at least during those hours. And if you take a look at the intraday prices, you can see a very interesting, very distinct pattern, especially if you compare the quarter hours of within 1 hour. So, and this is also relating to PV technologies because it's actually, it's depending on the rise and the set of the sun. So the sunrise and sunset. If you think about a typical PV in feed, it looks kind of like a normally distributed curve that you know from mathematics maybe. And during the first half of the day, you have the sunrise, and during the second half, you have the sunset. And this physical effect is even reflected in the prices that we see at the electricity power markets. So for us as PV traders, we have the problem that we need to forecast the solar in-feed and then translate our forecast into bits on the power market. And at the day-ahead market, we only can trade hourly products. So for the hours on the day-ahead, we will always try to trade the average forecast for 1 hour. It's reflected in the small sketch that you can see in the lower left corner here. The black line is the average for 1 hour, and then once we get into the intraday market, we are then able to trade quarter-hourly products, and here we then fall into a systemic problem because during the rise of the sun, so in the first half of the day, we will always have the problem that we have traded sold too much energy on the day-ahead market because of the rise of the sun. In the first quarter hour, the in-feed is usually lower than the average amount of that hour. So here we need to buy more electricity to come to basically comply to our schedule that we have sold on the day-ahead market. So we as an Kraftwerke have a systemic problem that for the first quarter hour during the rise of the sun, we will need to buy power. And all other PV traders within Germany basically have the same problem because they are all dependent on the physical rise of the sun. And that creates a surplus demand for the first quarter hours during the first half of the day. And if you take a look at the prices, at the quarter hourly prices, this is reflected here. The surplus of demand for the first quarter hour results in higher prices. And on the contrary, if you take a look at the last quarter hour for 1 hour, here we usually would have sold too few energy. So here we have a lack of energy after the day-ahead market. So here we will need to sell the surplus of in-feed that we expect from our PV plants. And again, all other PV traders have the same problem. And this surplus in demand does result in lower prices, which are also reflected in the typical quarter hourly intraday prices, as you can see them here in this graph. And once we have reached the peak of the PV in-feed, this whole effect turns around. So in the second half of the day, we have the same problem, but just in the other way. For the first quarter hour, our in-feed will be usually higher than the volumes that we have sold on the day-ahead market. So again, here we have a surplus of supply, and the surplus of supply, it does create lower prices in those cases. And then for the last quarter hour, we have a surplus in demand, and that again creates higher prices. So now I'd like to get into the topic of how those forecasts can help us to cost efficiently integrate large capacities of wind and solar. The intuition would be that if you increase the capacities for solar and wind, that this should translate into higher forecast errors, because wind and PV are very volatile and fluctuating technologies, which are hard to forecast, especially if you compare them to controllable power plants that are based on technologies like gas or coal. But if you take a look at the case of Germany, actually the contrary happened. On the right side, you can see a graph that shows the increase of wind and solar generation from the years 2011 till 2017. And here we have a very significant increase of generation of renewables by 110%. But during the same time, you can see that the sizing, so the capacity for frequency restoration reserve, which is needed to balance the electricity grid, the electricity network, have actually decreased by 50%. And if you take a look at the actual applied balancing energy that was needed, this even decreased by 55%, which is very significant. So here our intuition did not hold true. In fact, it even was the contrary, because although we have the capacity of wind and solar generation have increased by such a significant amount, we have been able to decrease the need for frequency restoration reserve, so for means of the TSOs to balance the grid. And two of the reasons for the decrease of those measures is the increase in the trade in quarter hourly products that happened since 2011, because quarter hourly products are way better to reflect this volatile profile of PV and also of wind technologies. You can see it on the right-hand side in the lower graph here. You can see how the volumes for the continuous trading in quarter hourly products and also the intraday auction in Germany that has started in 2014, the volumes, so the terawatt hours per year, they have increased from a bit higher than 1 terawatt hour in 2012 to almost 10 terawatt hours in 2017. And but to actually be able to cost efficiently integrate those large volumes, of course, you need a sufficient liquidity in intraday markets. Because if you only have PV traders that want to sell or buy their forecast errors on the market, then this won't help. You need other counterparties that are also active on the intraday market to be able to efficiently trade your PV volumes. And you also need a gate closure that is very close to the actual real delivery time, because the forecast becomes way more accurate the closer you get to the actual delivery time, because the weather becomes more certain basically the closer you get to the real time. So now I can make a way better forecast about the weather in 10 minutes than I can do about the weather in 4 hours, for example. And but this example can already show you that a cost-efficient integration is basically possible. It can even, a system can even become more cost-efficient if the markets that are put in place are set up in the right manner. And now I'd like to show you how we come up with the forecasts for our PV portfolio at Next Kraftwerke and how we can support the system via our accurate PV forecasting. Now, regarding the day-ahead forecast, it is unfortunately kind of impossible to make a precise forecast one day before the in-feed because the weather is still way too uncertain. So a good intraday forecast is important to be able to trade forecast corrections and to minimize imbalanced quantities. So here we make a kind of strict division between our day-ahead forecast and our intraday forecast. So the day-ahead forecast is mainly based on weather data, such as irradiation, temperature, and various models, weather models. We also have stored the technical data for each PV plant in our own internal databases. So here we need the orientation and the location of a plant and also the module type. And this forms basically, so the physical forecast basically forms the basis for our day-ahead forecast. And then once we get into the intraday forecast, this intraday forecast is then updated regularly, basically in 10-minute intervals, because we always receive new updates. We always collect new updates on the weather data and also especially on the live data, which makes a very important part of our intraday forecast. So for the live data, we collect the basically measured data at a certain technical unit throughout various connection systems. And here it's important for us to have fast and robust measures put in place so that we can collect the live data in a very efficient and fast way. And this needs to happen for thousands of plants. Our portfolio consists of almost 5,000 plants. So it's very important that those processes are robust and that they are also happening in a very fast way. And then we also take a look at the historical data of the in-feed. And this historical data is then used as an input for statistical algorithms, and those statistical algorithms, they work with the day-ahead forecast, with the live in-feed and the historical data, and that way we are able to come up with our intraday forecast. And in the following, I will focus on the intraday forecast and especially on the live in-feed, which is a very important part here. So when we do the intraday forecast, we often fall into problems and bottlenecks because we're facing technical errors when reading live data. And here we need to come up with an efficient way of correcting data where it is possible and to clean out data of plants that we cannot use anymore. So here we have some sort of layer of pre-processing for each unit, for each power unit, and that way we try to identify which units are feasible for our actual collection of live data. So you can see it here in the sketch. We filter out some units where we cannot correct the live data, and that way we are only collecting live data of feasible units. And those feasible units are then basically scaled to our actual PV portfolio by taking into account the nominal capacity of the whole portfolio. And that way we have an estimation of our actual live data for the whole portfolio. And this estimation for the live data is then combined with statistics and our day-ahead forecast. And that way we can come up with our intraday forecast. Regarding the collection of the live data, it's also important to be able to collect it from different data sources, because the loggers at the inverters of PV plants can be very different. So here we need to add some sort of abstraction layer to the collection of the input. And that way we are able to process all the live data in the same manner. And here again, it's very important to consider the processing time and the computing capacity, because we have over 5,000 units. So we need to have very efficient algorithms put in place to be able to achieve the goal of updating our PV forecast every 10 minutes, so that our traders always have the most accurate information needed for the trading. And now I'd like to show you like some examples how we can actually do this data correction. Very often we need to do some sort of plausibility check when collecting the live data to filter units that have feasible live data from the ones who don't provide feasible live data. Very often the raw live data signal from a single PV unit can be scaled in a wrong way. So in this graph, you can see the measured live data at a certain technical unit, which is shown by the blue line over the course of one day. So this is basically collected live the data. And then we have the red line, which is the corrected live data, and the green line. The green line is very often overlapping with the corrected live data, but this green line is the officially measured in-feed data as it is collected by the distributed system operators. And then what we do is we have an algorithm that takes a look back at the last 2 or 3 days. And here it compares how does the actual measured data, so the green line, how is it compared to our actually live data, so the data that is measured at the device. And then the algorithm tries to calculate a correction factor that it can apply to the live data to make it coincide with the measured data of the plant. And very often this can be successful. So that way, once we have this correction factor calculated, we can then apply this correction factor in basically live on our live data. And that way we can correct the live data in a way that we have a better estimation of the real in-feed. This is happening here in the upper example, and also in the lower example, we are able to correct the live data in a manner that it mirrors the actual measured data. And so in those cases, these are 2 units where we are able to make the live data feasible to consider it in our intraday forecast. But there are other examples where we are not able to correct the live data. Sometimes the signal freezes and we receive wrong data. And in those cases, it's important for us to identify whether data can be used or not, or whether we should filter it. And here are some examples where our plausibility check basically identifies that the live data that is collected at a plant does not match the measured data in the former days. And in those cases, we filter out those plants so that we don't run into any errors during our live data collection. And here I'd like to give you a real-life example on how our intraday forecast actually works. So here in this graph, again, you can see the course of one day. The blue line is representing the day-ahead forecast for our PV portfolio. Then the green line is our live data collection. So this is basically the estimated live data, which is made up of the feasible units. And then we have the intraday forecast, which is the green. So we have an expected value of the intraday forecast, which is the green, the yellow line. And then the yellow shaded area is basically a set of intraday forecasts, because we calculate a set of intraday forecasts by the combination of physical and statistical models. And as a result, we receive not only an expected value, but also a confidence interval that can provide traders with a measure regarding the certainty level at a certain time and place. And the parameters of the intraday forecast are then continuously tuned by the measured live data in the feed. For example, if you take a look at the peak of the live data that has been measured here at 12:30, and you can see that the last live data point that we have collected has been around 13:15. So our time, in this example, our time would probably be about 1:15 p.m. And at that time, the algorithm must have detected that the peak of our PV in feed has already been reached at 12:30, because after 12:30, all data points have been decreasing, are lower, below the peak. And then the algorithm basically, in this case, most probably has taken this result, so the result that the peak has already been reached, and has transformed it into an intraday forecast for the upcoming hours and quarter hours. So this results in the peak of the live data being transferred to the peak of the intraday forecast that is then shown for 13:30. And as you can see, the intraday forecast for the upcoming hours is then always below the peak at 13:30. And the forecast works quite well most of the time, as we have been able to put in place automated pre-processing and the development of very intelligent algorithms, which helped us to build up an expertise in also handling very vast amounts of complex data, because the data for each unit that is collected, it must be, this must be very scalable, the processes that are put in place, so that we are able to deal with such a large portfolio. Now I'd like to quickly sum up all of the main points of the forecast of the presentation, and that we can get into your questions. So, as Aleksandra has mentioned, virtual power plants are a very important means to promote the decentralization and also the digitalization of the whole power industry, because we are able to connect small decentralized assets such as generators and also demand side to aggregate them and to connect them to power markets and also ancillary services, so that they can offer different services and create an added value for the owners. And we support the owners by various products that we offer, and that such as forecasting and also the NEMOX software as a service. And this allows us to create a partnership with the PV plant operators to help them to profitably operate the PV technologies. Regarding the whole market, we have, I have tried to show you with the example of Germany, that the liquidity in well-designed intraday markets is crucial and also required to be able to cost efficiently integrate large volumes, large capacities of fluctuating renewable energies such as wind and PV into a certain market. And regarding the PV forecast at Mixed Kraftwerke, it has become clear that very smart and fast data pre-processing is required to efficiently be able to handle the data, the live data that is collected, because this live data then plays an important role when we come to the intraday forecasting. And we achieve a very accurate intraday forecasting by the combination of the live data and also physical models that are used in the day-ahead forecasting, and also statistical algorithms that can help us to effectively manage our portfolio and also to provide information to our traders in a very fast and efficient manner. And that way we are not able to help our traders, but also to reduce the cost and add value to the operation of PV plants for the operators. So yeah, I'd like to thank you for your attention. And yeah, we are now open for your questions. So yeah, thank you very much.